Okay, so next problem. A student weighing 572 newtons, well, we talked about in class, technically a weight is a force, and so it should be in newtons. Now, this corresponds to a mass of some kind, which we could find. We might actually end up finding that for the purposes of this, but we'll see. So they weigh 572 newtons, which would be probably around 57, maybe 58-ish kilograms would be the mass. You can solve for that if you'd like. They climb at a constant speed to the top of a 13-meter vertical rope in 17 seconds. What is the average power expended by the student to overcome gravity? And I say average because if you think about a student climbing in real life, they'll kind of go in small juts where you'll have, I get pulled up, then I stop for a moment, and then I get pulled up again, then I stop for a moment. What they're saying is just pretend that you're going up at a constant speed the entire time. We're doing an approximation of real life, but it should actually give us a pretty good value. All right, so I've got a rope, and I've got a person climbing up the rope. Now they tell us that the weight of the person is 572 newtons. So in short, what they're telling us is, the two ways that you could look at this, the force of gravity is equal to 572 newtons, or when they're standing on the ground, whatever force would be applied to them to get a zero acceleration, the force up, would be also equal to 572 newtons. In either case, we could, whatever you want to define weight to be, either be the force of gravity or the normal force or some other force in response and balancing out gravity. That would be, you'd still end up with the same thing. They want the average power expended, okay? They say that the person climbs up the rope at, 13 meters, and they do so in a time of 17 seconds. So in this case, there are a couple ways that we could go through and we could do this. First off, I'm going to do an extra step on this. You don't actually have to do this, but just to tie it into the way that we deal with things, they've given us the weight, and quite rightly, they have told us that the weight is in newtons of force. I know that Fg is also equal to mg near the surface of the Earth. So if I take 572 and I divide it by 9.8, or 9.81, I find that the mass is, hey, look at that, about 58.4 kilograms. In case you were interested in that, it also ties it together with the types of questions I ask in class. All right, there are two ways to go about this. First and foremost, we could say that the person is going up at a constant speed, so they're supplying the force upward, positive 572. So we could find, the first way that we do this is we say the work done by the student is they apply a force over a displacement, this time it'll be delta y because we're going up, times cosine of the angle between them. Well, the force that the student is applying, they're doing the work here, they're pulling themselves up. The force is up, and the direction that they're going is also up. So theta equals 0 degrees. They both point up, they both point the same way. So my work done is going to be equal to the force. Well, we know the force that they're applying, which is 572 newtons. Delta y, we know our displacement, which is 13 meters. And we know cosine of the angle between them, cosine of 0 degrees, which, when you plug it into your calculator, is just 1. So I get 572 times 13 meters, and I get the work done is going to be equal to 7,436 joules. The other thing that we've looked at in class, the power is going to be equal to the work divided by the time it took to do that work. So we have 7,436 joules divided by the time, which I believe was 17 seconds. Yep, there it is, 17 seconds. So we got 7,436 divided by 17 seconds. Joule divided by second is, as we talked about in class, a watt. The student supplies 437 watts during that time period. The work done divided by the total time that it's done in. Basically, it says how quickly the student, is adding energy into the system. In other words, converting chemical energy in their body into mechanical energy of potential energy in this case. So effectively, they're adding 437 joules every second. That's another way of looking at it. That's what a watt tells us. Now, the other way that we could look at this is we could say work is equal to delta E, and the change in energy that we've got, final minus initial, is going to be our potential energy due to gravity. Well, in that case, we would say that we started with no energy. We're going to say that we started at y equals 0. I'm going to do this a little bit faster, but it'll be equal to mg h, the height that we go up to. This is where that mass comes in handy. I told you that the mass was 58.4 kilograms. I've done that correctly. 58.4 kilograms, good. Times g, which is 9.8 meters per second squared. In fact, when you multiply these two together, that's the force of gravity in there, m times g. And so you're just going to get the 572 back. And then we're going to multiply it by the height, the new y coordinate that we get up to, which is 13 meters above where we started. When I multiply all this out, I'm still going to get, let's see, 58.4 times 9.8 times 13. This is just a formality, but we end up with 7,440 to the significant figures that we've actually got as joules. That's how much new energy the student has. They've actually released it from chemical energy stored in their body, but we're not solving that yet. So we're going to look at that as though it's new energy coming into the energy cups that we actually look at. So they've released chemical energy stored in their body and put it into mechanical energy, which is the kinetic and the potential energies together. In this case, they've got more potential energy. They haven't changed their kinetic energy because they're going up at a constant rate. And we then finish this up with the power being the work divided by the time, the change in energy, if you prefer that approach, 7,440 joules divided by 17 seconds. This will be a slightly different number, but it's just rounding error. Divided by 17, and we end up with, once again, 437 or 438 watts to three significant figures. Survey says 437 watts. Both of these would be accepted as correct answers. And they're both correct ways of looking at this problem. Work can be viewed as our change in energy, how much energy we've added or taken away, and it can also be viewed as a force applied over a distance.